Thanks, Paolo. Thanks for the organizers for giving me this opportunity. It's always a pleasure to be here in Pisa. I have to admit this is the first time I give a presentation holding a microphone, so I'll see how it goes. Okay, so the talk is about coupled systems, and these coupled systems are called coupled by collision. And in order to start my presentation, I'm going to start with a motivating model behind these coupled system coupled by collision. So this is a physical model which was introduced by Gaspard and Gilbert in 2008. Probably here the colors are not good, but the big circles, these are the gray circles, which I mention here as obstacles. So these are obstacles, and the small circles here, these are moving balls. So what happens here is that I'm going to have side dynamics on the lattice. So on each point of the lattice, I have a side. And so, for example, this one here will represent a side. And during the dynamics, it's when no collision happens, the dynamics is given in this model by classical billiard dynamics. So let me explain a little bit. What happens here when this ball is moving is the following. The balls are made in a way which are fat, that they can't go to the other side. They can't go through two of these obstacles, but they are thin enough to collide with another neighbor. And the collision only happens with one neighbor at a time. So as you see, this guy is here. It will only collide with this one if both of them are at the same position at the right moment. Okay? So this is the type of collision I'm talking about. So, as I said, when there is no collision, the dynamics is evolving according to classical billiard dynamics. And when two moving balls collide, they exchange the components of their velocity that are parallel to the line through their centers at the moment of impact. Okay, so this is the a motivating example. This is not the model that I'm going to study. The dynamics that I'm going to study will be simplified dynamics. It won't be billiard dynamics. And the geometry also will be much more simple. But this is a motivating example, which I hope to study in 10 years' time. Okay, so what do we want to study here? Actually, I came across this article by Lisa Young, which was written in 2013. This is a review article under this title, Understanding Chaotic Dynamical Systems, where she suggested the following line of research. So she wanted, in one of her questions, she was talking about large systems, and one of the questions is that if we increase the size of the system, of a large system, what happens to dynamical quantities? How do they scale? For example, entropy, and what happens to local dynamics? So in a sense, in a coupled system, what I understood from this and what I want to study is the following. So if I have a large system, I want to keep the size of the system as a parameter that I want to see how quantities scale with it. And if I know the local dynamics before coupling, I would like to see what happens to the local dynamics after coupling, meaning what happens at each site after coupling. Okay, so this is what I want to study. And coming back to the model which I've shown, this is the collision model. I want to study a simplified collision model, which is a discrete time one, and it was introduced by Keller and Livrani in 2009. Okay, that the features are very similar, but of course the Gaspard-Gilbert model is much more mathematically involved. Okay, so what do I want to do here? I want to quantify, so we're talking about entropy, so we'd like to see any information that we can get after coupling takes place and how such quantities scale with the size of the system. So one quantity when we have a collision is the following. I'd like to quantify orbits under the dynamics that do not see collision up to time n in a lattice of size L. So this is a parameter for me. The size of the lattice is a parameter, and I'd like to see how this quantity scales in L as the size of the system grows. Then the hope is to derive a formula for what I will call the first collision rate, and I want to do this per unit lattice. Okay, so this is the outline and the motivation of what I want to do and the question that I would like to answer. Now I'm going to introduce the model. So this is, again, I repeat, this is a model which was introduced by Keller and Livrani. So the site dynamics here on each point in my lattice, I will have a dynamics, and the dynamics will take place on the unit interval. And I'm going to consider a finite dimensional lattice, so I take lambda copies of the unit interval, and I place them on a finite dimensional box of the d-dimensional lattice. I'm going to denote by ML the L-dimensional Lebesgue measure. Okay, so here is the site dynamics. So this is the evolution of the dynamics on each site. It's given by a map from I to I, and I denote this by tau. If you are coming from physics background, this is just a chaotic map. Think about it like this. But if you are mathematicians and from my close community, I'm assuming that this is piecewise monotone onto expanding and C1 plus alpha. Okay. And then the uncoupled dynamics on the whole system will be given just by the product map. And well, what's the product map? This is a T0 applied to a point X at site P. This is just the local dynamics applied to XP. So this is the uncoupled dynamics. And now we want to introduce the coupling. Okay, so we talked about coupling by collision, and this is, remember the picture which I've shown you at the beginning, the Gaspard-Gilbert model. So what do I want now? I want to put, I have a site and I want to put directions. Let's say I'm in a one-dimensional lattice, so I can collide with my right-hand side neighbor or with my left-hand side neighbor. If I'm in a two-dimensional lattice, I have 4 directions to go. Okay, left, right, up, down. And so this is the job of these V plus. These are the, just to tell me the directions. And V plus will be the standard basis of RD. And then I have to define collision zones. So on each interval, I take a small epsilon bigger than 0, and I take the following disjoint subintervals of I, and these are open disjoint intervals, each of length epsilon. Disjoint is very important because in the model that I described before, we said that you collide with one neighbor at a time. So they have to be disjoint, these intervals here. And the coupling looks as follows. So this is phi epsilon at x. This is the coupling map at site P. What happens if at site P the dynamics enters to the zone A epsilon V, and the right neighbor enters to the right collision zone at the same time? What happens is that they exchange, we exchange the exponents. If this does not happen, then I just apply the identity map. So such coupling is interesting from many points of view, in particular mathematically. As you see in coupling, usually it's assumed that the coupling map is smooth and it's close to the identity in some CK. And here, as you see, the coupling introduces discontinuities right away, and this is only closed in L1. So it has interesting features. So even if you start with smooth local dynamics, this will destroy smoothness right away. Okay, so the coupled dynamics then is defined as follows. This will be denoted by T epsilon. And T epsilon is nothing but, okay, so you take the uncoupled dynamics, the product map, and you compose this with the coupling. All right, so what did we prove? Well, I want to look at first collision rates. So I want to look at orbits that once they collide, I want just to neglect them, and I want to count this, and I want to see how this goes. This is very similar to what Sandro was talking about holes. Okay, so I can, if I want to study the problem of finding a formula for a first collision rate, then I can view now this property as a rare event property, and I study kind of an open system. In particular, if you will, maybe I'll get a question about this, but before getting a question, in what I'm going to study, it doesn't matter how this coupling is defined here. I can put any function and I still get the same result. All what I care about, I want to count the first collision rate. Yeah, it doesn't matter whether they exchange velocities or you take the average, it's the same problem for me. I'm only counting the first collision rate. Okay, so for this, now to view this as an open system, as I mentioned, I consider the following sets. So for P on the lattice, now I'm going to remove the set of points at site P in direction V that do not see a collision. And then if I take the intersection in all directions and in all sites, this will be the set of points that did not see a collision at time 0. Okay? And if I take the intersection of these pre-images, this is the set of points that did not see a collision up to time n. Okay? And now we can, so the complement, I denote the complement by H epsilon because this is, as I said, I can see this as a system with holes. So H is for a hole. Fine. And we can define the following limit. So we say, suppose that the following limit exists, and here I do the limit with respect to a Lebesgue measure. If this limit here exists, then we call such quantity the first collision rate under T epsilon with respect to Lebesgue measure. Okay. So this is similar to what we call escape rates. So what we prove the following. We prove that the first collision rate of T epsilon with respect to Lebesgue measure, it exists. And in fact, it has the following asymptotic formula. So this is mu0 of H epsilon. H epsilon, remember, this is what I call the hole, times theta, which is a constant. Typically, it's 1. And in other situations, it has other values that I'm going to illustrate in a minute. 1 plus little o of 1. And what is mu zero? Mu zero is just the product, the product measure of the local dynamics. So this is the absolutely continuous invariant measure with respect to the product map. But what we want, because we want to see the statistics at the micro level, at the site level, I'm interested in seeing how this quantity, not only asymptotically how it behaves in epsilon, I want to see how it scales in L. And for this, we derive that mu zero of H epsilon actually scales linearly in L. So it's L into psi epsilon. And this psi epsilon is given by the following formula. So this is the invariant density of the site dynamics. Yeah, and this is integrated over the collision zones. Good. So since I see that this quantity scales linearly in L, I can easily now deduce a corollary how the statistics, in particular the first collision rate per site, what is the formula for such a quantity per site. Okay, before going to that, I'd like to mention that this theta is a pretty interesting number. Sandro mentioned in his presentation in extreme value theory, this is called the extremal index. And in this situation, actually, the theta, typically it's always 1, and we know this. But in certain cases, you get different values. And what happens here in this model, that if you are on a one-dimensional lattice, you get a pretty simple formula. But if you take a higher dimensional lattice, you get an interesting formula. Okay, so since, as we said, this scales linearly in L, I can easily now derive a formula for the first collision rate per lattice unit. And this will be simply just divide what we got by 1 over L, and this is an explicit formula. So this is my goal. This is what I wanted to do. I wanted to see if I can get information about the local statistics as the size of the system scales. So it doesn't matter here what size of a system I take. This is the formula that I get per unit lattice. However, I'd like to remark something, that this little o notation, there is a dependency on L in it. Yeah, so there is an L hidden in the little o of 1. Okay? Not xi. Xi is there. So xi is about the directions. Which one? The strength also no. No, the strength is just the size of the collision zone. Okay, so this is the thing, and now let me show. This is all what I wanted to talk about. One more thing, I'd like to go back to this theta. So as I said, typically theta is equal to 1, but let's say we are in a situation where we have a one-dimensional lattice only, and I take, so I have only 2 points in this set S. This is where the collision zones shrink to. These are the points. So I only have one point like this, and if this point here is periodic of period k plus 1, then this is what I get. And this is very similar to what you see in one-dimensional dynamics. However, if I go to a d-dimensional lattice, and I have some of these points returning to S, this is the formula that I get. Okay? It was the first time I see something like this for this extremal index, and I find this interesting. Okay. This is all what I wanted to talk about. Thank you very much.
So, questions, comments? So, can you explain me again how come the strength of the interaction doesn't matter at all in your.
It doesn't matter in the following sense. Epsilon is sufficiently small. Yeah? Everything which is done here is done through perturbation theory of transfer operators. So epsilon is sufficiently small.
So basically the interaction is as small as you need it.
Yes.
Okay.
Yeah.
Thanks.
And this is far away from this synchronization business and epsilon being big.